So let's take a look at this. What I'm going to do here is show you several different ways that you can approach this, okay? And so that you can kind of see the process or kind of the systematic approach that I would encourage you to use. All right. Anytime you're doing a proof, obviously you always start with the given. So I started with the givens in each of these different cases. Okay? Let's start with the first case. Regardless of the proof, what I would encourage you to do is look to introduce the end state elements as early as possible. And when you introduce them in the most simplified form that you can. And so when you look at this, our end state elements of AD and BE. Okay, so if all I know is this given information that AB and DE are equal, if we can introduce AD in terms of either AB and or DE and introduce it by itself, okay, that would be the ideal approach. So if we looked at AD, we can think of AD one of two ways. We can think of AD as being the sum total of some parts. So if we looked at that, what we would probably see is that this already introduced part AB can be added together to this part BD to give you the whole thing AD. So that's one way to look at this. One way is to say that AD is equal to the sum of the parts AB and BC and BD. Hey, what justifies that statement? That's the true form of segment addition, right? Okay, now at the same time, so that allowed me to introduce AD, I can introduce BE. BE also is sum of parts, the given part DE plus the unknown part BD. So I can do the same thing. I can combine this in the same step here. BE is equal to the sum of the parts DE plus BD. So regardless of how I approach this or what I do next, this is a very useful first step. And I'm gonna show you two different ways to look at this. And so I'm just going to copy the same thing here. This is looking at it as my my end state. I'm thinking of it in terms of the whole thing, right? The whole made up of individual parts. And so even within that, I have two different ways to approach this proof. Okay, one possible way to approach it is to transform, or again, in order for AD and BE to be equal, I somehow need to show that the expressions that AD and BE are equivalent to are somehow equal to each other. So if I took, let's say, this statement, AD is equal to AB plus BD. Okay, so I'm going to manipulate it here. I just want you to see what I do. Okay, so if I take this statement, all I've done is I've copied that down. But what can I replace AB with? What is AB equivalent to based on my proof? So I can erase this. I can take away AB and I can replace it with its equivalent DE, right? So by doing that, direct replacement is called substitution. So I just substituted in AB with its equivalent DE. And what that wound up doing is it now winds up saying that I have two things, BE, I have BE and AD. I have two things that are equal to the same thing, DE plus BD. They're both equal to the exact same thing, therefore, how are they related to one another? Things equal to the same thing are equal to each other. So I have my final statement. I can say that AD is equivalent to BE. And the justification for two things equal to the same thing or equal to each other is called transitive property. Now, I could have also just said, I could have just copied this statement 3 down. AD is equal to, and what is DE plus BD equivalent to? In step 2, it's equivalent to BE. So I could have just directly substituted that as well. So this is one potential way to approach this problem. Okay, let's look at a different way even if you saw the first step as AD, this end state element being the whole thing, it's made up of individual parts. There's still another way that we could have approached this, and that is it's still based on the idea that in order for AD and BE to be equal, their equivalents need to be equal also. So what if I took statement 1? So what if I wrote AB is equal to DE? Now notice I left a little space here, because what I want is when I look at these two statements in step 2, AB plus BD and DE plus BD. So if I look at those, what can I add to this first equation to get this form? I simply add BD, right? So if I add BD to one side of the equation, I need to add its equivalent to the other side. So its equivalent is either BD itself or something that BD is already equivalent to. So what if I just added BD to the other side as well? That balances my equation. What did I do to both sides of the equation here? When you add the same value to both sides and it maintains its equality, that is addition property. And then now what can I replace? So now when I look at this, what is AB plus BD equivalent to? It's equivalent to AD, so I can replace that with an AD. And what is DE plus BD equivalent to? In statement 2, I see it's equivalent to BE. So once again, I wound up arriving at my final end state. This time, when I did this, I replaced equivalent values, and replacing is just a matter of substitution. Okay, so here's two possible ways. Both of them are built on the fact that we saw AD, that end state element, as a whole made up of individual parts. All right, let's go back and see what happens if we think of it in the other direction. Hey, what if we don't think of this as this end state being a sum of parts? What if we think of it as being an individual part itself? So what is AD a part of? What whole? AD is a part of this whole AE. So we could also say AD is equal to the whole thing AE minus this other part DE. So we could have written statement 2 as being, again, notice, instead of me saying, I'm not saying AD plus DE equals AE. What I want to do is I want to isolate this part AD. Whatever your end state elements are, isolate them. So AD is equal to the whole AE minus the other part, DE. And what would justify that? Okay, now we are subtracting here, but remember, segment addition has 3 forms, right? Really 2, but the 2 forms are the sum of the parts equal the whole, or the part equals the whole minus the other part. Is this equivalent to the part AD equals the whole AE minus the other part DE? Yeah, it's still an interpretation of segment addition. So even though there's not a plus symbol, even though you see the subtraction symbol, this is an example of segment addition. Okay, so that allows me to introduce the element AD. I can do the same thing with BE. BE is a part to the whole AE again. So if I took BE, BE is equal to the whole AE minus the other part AB. Okay, it's still segment addition. Okay, so once again, in my last 2 proofs, they're going to both start with this premise, that you saw that relationship to introduce your end state. Okay, in either way, it's segment addition. Okay, so let's go back to this one and see what the last 2 steps would be. All right, so one way that we can approach this is the same thing that we did up here in the purple. And what if we take one of these 2 equations from step 2? This time I'm going to take the second one. Again, it doesn't matter first or second. It can be either one. But if I took BE is equal to AE minus AB. And what if I took that equation, so that's just copying it, what can I replace AB with? What is AB equivalent to? I can replace that AE with its equivalent DE. Okay? And so that is just a replacing, substitution. And what you can now do, you have two things, AD and BE, that are equal to the same thing, AE minus DE. So if two things are equal to the same thing, they're what compared to each other? They're equal to each other. So AD and BE have to be equal, and the reason is transitive property. Now, we could have just taken this statement, copied the AD down. AE minus DE we saw is now equivalent to BE, so we could replace that directly. So this could also be called substitution. Right? Either of those forms is fine. Okay, but you do need to be able to recognize when it can be either. Anytime transitive property works, substitution would also have worked. All right, now if we're thinking of it more similar to this red pattern, where in order for these two expressions to be equal, the values that they are set equal to have to be equivalent. What we would need to do is somehow show that AE minus DE is equivalent to AE minus AB. And so we do need to introduce AE. We don't have AE anywhere else. So if we set up an equation where AE is equal to itself, anybody remember what that's called? Reflexive property, good. Okay, and then if we took this equation, AE is equal to itself, and we subtracted a DE from one side of it, what would we have to do to the other side to maintain the balance? We'd have to subtract DE or its equivalent. Well, what's equivalent to DE? AB. So if we subtract equivalent values from each side of an equation, the equation remains balanced. That is subtraction property. Okay, and then here we wind up with this one additional step. Okay, and so if you look at this, AE minus DE can be replaced by its equivalent AD, and AE minus AB can be replaced by its equivalent BE. And so replacing is just justified as substitution. Okay, so here are 4 different ways that you can approach this proof. Any of them work just fine. Basically, all of the proofs that you're going to see on this worksheet will be some form of this. You're pretty much, these are the reasons that you're going to use. Segment addition, addition property, subtraction property, transitive property, substitution. And that's really about it. Okay?